Okay. So for today's journal club / seminar, we're happy to have Ranveer Singh. He's currently a student at Rutgers, but he'll be joining the group as a postdoc in the fall. So go ahead and take it away.
So thank you for the invitation to give a talk here. And I'm looking forward to be here. It's really nice. Today I'll be telling you about a couple of papers that I wrote to compute certain indices in 4n equals to 2 superconformal field theories. And I'll tell you about two techniques that we developed to do these computations. So, and it is based on these two papers. Right, so here is the outline. So I'll very briefly tell you what superconformal indices are. Then I'll explain a few limits of the superconformal index, which are easier to compute. And then I'll explain a recent correspondence between SCFTs and chiral algebras, which can be used to compute one of those limits of the superconformal index called the Sur index. There is another limit which is called the McDonald index. And one of the main parts of the talk will be to explain how to compute McDonald index from chiral algebras associated to the SCFTs. And then in the second part of the talk, I'll explain a recent conjecture to compute Sur index using something called the monodromy operator. And then I'll explain how to generalize it for a special class of theories to compute McDonald index from monodromy operator. And then I'll end by explaining the future directions. All right. So here is a very brief definition of the superconformal index. So in 4n equals to 2, the superconformal algebra has, of course, the Lorentz group, which I'm taking it to be Euclidean. So it's SU2 times SU2. And the Cartan generators of these two SU2s I will denote by J and J bar. Then there is a scaling transformation, whose Cartan generator I'll denote by capital E. And then there is SU2 times U1 R symmetry. Their Cartan generators are capital R and small r. Then there are Poincare supercharges and conformal supercharges. And then there is also spatial conformal transformations. So with these Cartan generators, one can define this superconformal index. And here P, Q, and T are formal variables. And they are fugacities for these charges here. And F is the fermion number. And we are computing the trace on the Hilbert space on S3. So we are considering the theory on S3 times S1 and computing the trace of the Hilbert space on S3. And now one can show that this index actually gets contributions only from 1/8 BPA states. And in general, one can also allow for flavored fugacities if the theory has flavor symmetries. But for now, I'll just set them to be 1. Later, we will introduce them. Right. So now one can take certain limits of the superconformal index. One particular limit is this McDonald limit, in which we take P to be 0. And then if you look at that definition, taking P to 0, only those states which have J minus J bar minus R equals 0 will contribute to this index. And then once you factor that into the formula, you get this formula for the McDonald index. J and J bar have completely dropped out. And these count quarter BPA states. Now, one can also take the Sur limit. So you can take this limit T going to Q either in the full superconformal index, or you can take this limit in the McDonald index itself, and you get the following formula for the Sur index. T going to Q limit in the McDonald index is clear. If I take T going to Q, these charges combine and I get this formula. But in fact, one can show that if you take T going to Q even in the full superconformal index, then also the P dependence drops out and you get the same formula. So I can get the Sur index either from the McDonald index or from the full superconformal index. So this also counts quarter BPA states, but it has less information compared to McDonald index, because McDonald index also counts, also has information about this capital R plus R charge of the states, but Sur index only has information about capital E minus capital R. Right, and as I said, the Sur index can be obtained from McDonald index by taking this T going to Q. Now, there are various indirect ways of computing the index. There are several techniques, and I'll be explaining two of these techniques. One of them is this SCFT VOA correspondence, And the other one is this using the monodromy operator to compute the index. All right. So let me very briefly tell you about the SCFT BOA correspondence, because that is something which we will be using. So under this correspondence, given any 4D n equals to 2 superconformal field theory, one can associate a 2D chiral algebra or a vertex operator algebra. And under this correspondence, these spatial operators in the superconformal theory called Sur operators. The Sur operators are those operators which satisfy this particular relation. So their charges satisfy this relation. And these Sur operators correspond to chiral operators in the 2D chiral algebra. And the conformal dimension of those chiral operators is given in terms of this E and R charge of these Sur operators in 4D. And there is a particular operator in the 4D theory in the stress tensor multiplet. And one can show that that operator is a Sur operator. So it will correspond to a chiral operator in 2D. And this particular operator corresponds to the stress tensor in 2D. So we already have enough information to say that we have a chiral algebra because we have a stress tensor. And the 2D central charge is related to the 4D central charge via this relation. So the 2D chiral algebra is already non-unitary because of this negative sign. And then if the 4D theory has flavor symmetry, then it will have flavor multiplets. And then there are operators in the flavor multiplet which map to Cass-Moody currents in the 2D theory, so in the chiral algebra. And the level of the Cass-Moody current is again determined in terms of the level of the 4D flavor multiplet operator. Now you can see that the conformal dimension is of the 2D operators is E minus R. And you can notice that in the Sur index, we have that same E minus R appearing here and -1 to the F. So from that, it's more or less clear that the Sur index is given by the vacuum character of this 2D VOA. So once we can identify the VOA of a given 4D n equals to 2 SCFT, we have a way to compute the Sur index. All we need to do is compute the vacuum character. Let me quickly give you an example. So this will be the recurring example in this talk. So we'll be looking at a class of non-Lagrangian theories called Rutgers-Douglas theories. The general such theories are labeled by 2AD Lie algebras. And they can be constructed in various ways. Again, I'll not go through the construction, but now if there are two such theories which I'll be interested in, the A1, A2n theory. So A1 is just the SU2 Lie algebra. A2n is again SU2n plus 1, I suppose. Yeah. And the chiral algebra for A1, A2n Rutgers-Douglas theory is just the Virasoro algebra with the central charge. And the chiral algebra for A1, B2n plus 1 Rutgers-Douglas theory. So A1 and B2n, these are the two Lie algebras which label the 4D theory. And that chiral algebra is affine SU2 at this particular level, 4n over 2n plus 1. So these will be the two examples that I'll be interested in. Now, if I want to compute the Sur index of A1, A2n theory, all I need to do is compute the vacuum character of Virasoro VOA, which we have general formulas for. And again, for A1, D2n plus 1, the Sur index can be computed using the character of affine SU2. Again, we have explicit formulas for those. So, right, and here are some formulas. So you can compute the Sur index in various ways. This formula is from one particular way of computing the Sur index for A1, A2n theory. And similarly for A1, D2n plus 1 theory, this is the Sur index. Again, these are some notations. This is the Q-Pockhammer symbol defined by this product. And one can show that these formulas actually match with the vacuum character of the corresponding units. So, yeah, so that actually gives us new Q-series identity. If we can compute the Sur index in two different ways, then we have Q-series identities because they must be equal. All right. So now the question is, can we also get the McDonald index from VOA? Because now the McDonald index has more information compared to the Sur index. So now the question is, can we get the McDonald index from the VOA? And there is a partial answer, which is we want to look at the refined character of a VOA. Now, I'll not explain what refined character is, but I'll give a formulation in terms of, I'll give an algebraic formulation of the refined character, and that will give us the McDonald index of the 4D theory.
Remind us what more information the McDonald index has compared to the true index?
Oh, it also counts the capital R plus R charge of the states. So if you just compare with the definition here, then this is the McDonald index also has this capital R plus R charge, but the Sur index does not have any for that. But they count the same operators. So before I move to this part, I'll have to introduce a few definitions which can be technical, but are there any more questions at this point?
How does the R symmetry show up in the 2D BOA? Because the current doesn't match anything. So how
Yeah. So I'll be talking about that. That's why I said it's a partial answer. It's not a full answer because we don't have an answer to that question.
Can I ask, do the non-vacuum conductors in the BI have any meaning in 4 dimensions?
Yeah, so there are a few papers which compute the Sur index, but with insertion of certain defect operators. And when you compute those, then those are related to other modules, characters of other modules of the 2D chiral.
In 4 dimensions, it means you're computing a superconformal with
some insertion. Yeah.
Surface defect.
Surface defect, yeah. All right, so I'll introduce some definitions. This is a formal definition of a vertex operator algebra. I will only introduce the important stuff, but if you're interested, we can talk later about other stuff. So vertex operator algebra is this vector space which is graded by half Z. Either it's Z or half Z, depending on whether you're looking at algebra or super algebra. And then for each vector in the vector space, you have an operator. This can be thought of as the state operator correspondence. For each vector, I have an operator, field, and that can be expanded formally. So Z here is a formal variable, and VNs here are operators because these fields will act on the vector space again. There is a special vector called the conformal vector, which will correspond to the stress tensor of the VOA, and these LNs will satisfy the Virasoro algebra with some central charge. And note that the exponent here is shifted by 1. It's not just minus n minus 1, it's minus n minus 2, which is the usual notation that we use in physics. And then there is a vacuum vector, of course, whose vertex operator is simply the identity. And then if you act any vertex operator on the vacuum, you should get back the vector. So these are all inspired from physics. And then in physics, we also have operator product expansion, locality, and so on. So one can formulate those things mathematically in a formal way using formal variables. But I'm not going to tell you all that because that won't be necessary for what I'm going to talk about. Yeah, but there are some other examples regarding OP and so on. So one more definition is of what are called strongly finitely generated VOAs. So what this means is that I have a finite number of vectors in the VOA, U1 to U capital N, such that the entire vector space can be generated by the modes of these vectors. So I can keep acting these modes on the vacuum, and that will generate the entire vector space. Of course, I'll have to mod out by null vectors, but the entire vector space can be generated by these vectors. And these U1 to UN, these will be called strong generators. And a good example to have in mind are affine VOAs or Virasoro VOAs. Because for Virasoro algebra, we only have the stress tensor and LS generate the entire space. So it only has one strong generator. For affine VOAs, we have the number of generators is the dimension of the Lie algebra that we are using. And of course, these were the two examples that I mentioned earlier. So for those examples, the VOAs are strongly finitely generated. Okay. Another definition is what is called a zoo algebra. So given any vertex operator algebra, you can define this space. So what I'm doing is I have the vertex of the vector space here, and then I'm modding out certain subspace C2V, which is defined as follows. So I take any two vectors and I look at the A minus 2 mode of this vector. So what this means is that I look at the vertex operator here for A, and then I look at A minus to this mode here, okay? And then I act it on the other vector B. Now I look at all such vectors in this space and I mod it out. So this is called the zoo algebra. This construction seems very ad hoc, but actually it's very useful because what one can show is that this zoo algebra is actually a commutative associative algebra. And if you want to know about all irreducible modules of the vertex operator algebra, there is a one-to-one correspondence between those and modules of this commutative associative algebra. So to get all modules, all you have to do is classify modules of this algebra, which is much better understood compared to VOA modules. That's why this algebra is important. And for strongly finitely generated VOAs, one can show that the algebra is actually a polynomial ring, where these x1 to xn, these are variables corresponding to the strong generators. So you take the strong generators, map them to these formal variables, and then you mod out by the null vector relations. So null vector relations, basically, if I have a vector, if I have a null vector, I look at the terms, and those terms will give me a polynomial in these variables, and then I'll just mod out by those polynomials. So that's the zoo algebra for strongly finitely generated VOAs. And then, for example, the example I was looking at, the Virasoro algebra, which corresponded to A1, A2, N theory. The zoo algebra is simply this polynomial ring, Cx, modded out by this x to the n plus 1. And similarly, for the affine VOA, SU2 at level 4n minus 4n over 2n plus 1, the zoo algebra is generated by 4 generators. Actually, it can be generated by just 3 generators because SU2 has 3 generators, right? SU2 is 3-dimensional. So I can only include 3 generators here. But I also include this J here, which I'll clarify by. And then you mod out by these polynomials here. So F1 here you can see is xz minus y squared minus J. So J is related to x, y, and z in this bilinear way. It's not exactly bilinear, but it's quadratic. So one can identify this J with the stress tensor because the stress tensor in affine VOAs is given by the Sugawara construction, where you write the stress tensor as bilinears in other generators. So I also included this J because that will be useful in the computation. There is another technical reason, but I'll explain that later. All right, so this is just an example. Now we are done. There is one more definition that I need to introduce, which is arc space of a polynomial ring. I promise at the end of all this definition, we'll have a nice result. It looks very technical, but it will give us something nice. So what you do is you look at this polynomial ring. You will have some variables and then some functions which you mod out by. And then what you do is assign some weight to each of these formal variables, say di, okay? And then write this formal power series. Now, instead of capital N number of variables, I have infinitely many variables. So for each I have infinitely many variables here, x and I. And then I look at this space Rn. So what is this space? I take all these variables up to n, up to small n, for all of these small i's. And then I mod out by in. This in is obtained from these functions f1 to fk by just plugging in this infinite sum in that and just setting it to 0. So I will look at till order n, and whatever relations I get, I'll just mod out by them. So I'll give an example which will clarify this. This seems very technical, but the example will clarify what this Rn is. And you can ignore these two because these two will not feature in whatever I'm going to say, but you can define this jet scheme and arc space. It has its own usefulness. But let's ignore this for now. All we need is Rn and In. So then you can define this Hilbert series for this. So what you do is you just take this Rn, and in Rn you look at homogeneous spaces with respect to a bigrading. And this bigrading is given by this. So you take the variable xji and assign it this bigrading. First is just j, which is this index j. And the second is this weight, which again one has to introduce. Now, this is why I said it's a partial answer, as we will see later. But this is right now not defined. Like I don't know what to pick. One has to choose this for a given theory. But suppose you define this, and this is related to this problem called R filtration. I'll have something more to say later. And then you can define this Hilbert series. Okay. So what you do is you take R infinity, which is you just take all possible variables, all possible relations, and you count the number of generators according to this by grading. So you fix an L and M, and then you count how many generators you have at fixed L and M. And this Hilbert series, later we will see, will be related to the McDonald index. So there was a lot of definition, but at the end you get a nice Q and T series, and this will be related to the McDonald index. Let me just give you one example, which is this A1, A2 N theory, but with n equals 1. So A1, A2 theory. The VOA in this case was Virasoro, and the zoo algebra was just Cx mod x squared. And if you choose Wx equals 1, Wx is this weight that I did not define, then the Hilbert series can be computed exactly. This is what it is. And this agrees with the McDonald index of A1, A2 theory. So that is one observation. And this was understood in this paper by Boykin, Nishnata, and Bhargava. Another example which I will be interested in is this A1 D2n plus 1 example. That is a little more difficult because the zoo algebra in that case is given by X, Y, Z, J. I have 4 generators and these relations. But again, what one can do is, okay, so there was one more weight here which I did not introduce earlier, which was this DI, right? So for each of the variable, you have to introduce this DI, and this DI will tell us what this n starts from, whether this n starts from 1 or 0. So in this case, the DI was simply 1. X, the weight for X was 1, and Wx for X was also 1. So I have 2 unknown quantities right now, which is this DI and this Wxi. Both of them were 1 in this example. In this example, I have 3 variables. The weight for all of X, Y, Z is 1. For J, it's 2. And now you can guess what this is. This is simply the conformal dimension of the corresponding generator. X, Y, Z correspond to the 3 generators of SU2. And J corresponds to the stress tensor. So this weight is simply the conformal dimension of the generator. And then the W, I choose 1 for all 4 of them. And then we have this formal series, as I explained here. Like we have this formal series for each of the variables. So now we have formal series for each of the 4 variables. All these 3 start from 0, but this starts from 1 because the conformal dimension is 2 here. And then I have to consider these rings. So at order n, I have to look at all these variables till n, and then model by in. In is obtained by plugging in this formal series in these functions and setting it to 0 till order n plus 1. Okay. So for example, I0 will just be this because at I0, I0 is at order 0. So I only have to look at the constant term in S. I plug in this formal series in here, and then I look at the constant term in S. And the only such term comes from this first polynomial, because all of these will have J0, 0, because I don't have a J0, I only have J1. Okay. So all of these will not contribute anything. This will contribute to this polynomial. So that is the only constant I have at order 0. At order 1, again, you can write down all constant that comes from these 4 functions, and these are all of them. So once I have this, I can simply count, right? Now I look at order 0, 0. So the second index is telling me the degree. So yeah, here. So this m is telling me the degree because the power of t tells me how many variables I have to choose. And the first index is telling me what these subscripts must be. Okay. So for example, if I look at R00, then there is only one such polynomial, which is just 1. Degree is 0, and also the lower index, the subscript is 0. At degree 1, I have 3 generators. I don't have J1 because that would contribute to R infinity 1, 1. That won't contribute to R infinity 0, 1. So I only have 3. And then at all n greater than equals 1, I have these 4 generators. Okay. And I don't have any constraints right now because the I0 itself is quadratic degree, like it's degree 2. So that won't contribute. And this will give me the following Hilbert series till order t squared.
Notation on that, so R infinity, what is 0, 0? What are the two numbers?
Yeah, so these numbers are coming from here, here. So you look at, so I assign this by grading to these variables. Now all I have to look, the first index here is telling me which xj's will contribute. And the second index is telling me what should be the degree of the monomials that will contribute, depending on this w. But here I have chosen all of the w's to be 1. So it is just telling me what degree polynomials I have to look at.
What is W going to be eventually?
Sorry?
What is W going to be eventually?
Yeah, so
it's just 1.
yeah, at the end it must be related to the R charges in the UV. But yeah, we don't know what is the exact relation. That's why it's a partial answer. It's desirable to know the exact W for any given theory. But right now it's more or less experimental. You look at a theory, you assign some weight, and then you see whether you get the correct answer. So, right. So, yeah. So at order 0 and 1, I have this answer. I can determine higher order terms. And that is again some counting. I'm not going to tell you the exact counting, but one can do it. And you get these numbers. There is also a very systematic method to count these using Grosvenor basis algorithm. Let me ignore it because it's very complicated, but the upshot is that you can do all this using Mathematica. It gets complicated, but in some cases, you can actually get an exact formula. For example, in this case, for A1-D3 theory, this was the zoo algebra for A1-D3 theory, and you can get the exact Hilbert series in this case. And one can check that this actually matches with the McDonald index of A1-D3 theory. So these two examples motivate this conjecture, which is that you take a 2D, you take 4D equals to 2 SCFT, look at its VOA VT. Now it's conjectured and checked in various cases that this VT is actually strongly finitely generated for any given 4D equals to 2 SCFT. So you can look at its zoo algebra, which will be
other examples for that, or it's believed to be true always?
It's always true. Like we don't have any counter examples as of now. So its zoo algebra will be of this form. I'll have finitely many formal variables corresponding to the generators. I'll have some null vector relation. I look at its zoo algebra and then assign this grading, this weight that I talked about very early on when we have to write down the formal series. This Di is simply the conformal dimension of the strong generator. Then the conjecture is that there exists this Wxi. I don't know how to pick it exactly, but the conjecture is that one can always choose such Wxi's such that the McDonald index is given by the Hilbert series of the arc space of the zoo algebra of the
They're not
VOA.
somehow trivially related to the arch argument.
No, yeah, it's not clear what W's to choose. In most of the examples that one can work out, it's 1. In some examples, it's half as well. But in general, it's not clear what to choose. Like there is no general rule. And for some cases, for example, if you can have a free field realization for the theory, then there is a way to choose these Wxi's. And in those cases, this thing works well. But in general, there is no understanding of how to get these Wxi's from 4D. One would like to understand it directly from 2D, but right now it's not well understood.
I just asked something about the finitely generated. So it's usually one would want to take the spectrum of A, right? You want to interpret that as the Higgs branch.
Yeah.
Presumably that interpretation requires this strong finite.
Strongly finitely generated?
finite,
Yeah. So there are conjectures where just the spectrum of the zoo algebra should be related to the Higgs branch. And again, it is related to what is called like the free field realizations of the theory. You can use the free field realizations to check that it is true for most of those theories. But in general, it is believed that there are finitely many generators. Right. So now one good thing that comes out of this conjecture is that you can take the Sood limit in the McDonald index, which is send T to Q, and then you should get the Sood index. And if there are other ways of computing the Sood index, then you will have some new identities. And it's true for A1, A2, N theory. If there are other ways of computing the Sood index, and you take the Hilbert series, take T going to Q, you get these Rho-Straman identities. And for our example, this A1D3 theory, you get this particular Q series identity by looking at the Hilbert series that I showed here. All I have to do is replace T by Q, and then I get this series on the right-hand side, and this is the Sood index known from other computations of other computations. So these two must be equal. And in fact, one can prove that this is true. Yeah, and there is a version of such an identity for each n. This is only for n equals 1, but for each n you have such a identity. The right-hand side changes a little, it becomes a little more complicated. But you have new identities for each n.
So McDonald index been computed using other methods?
Oh, yeah. There are various other computations of McDonald index. For example, for A1, A2, N theory, it can be computed by other ways. And then you can check that it matches with this computation as well.
And the full superconformal index.
The full superconformal index can also be computed.
So all using that?
Yeah. Like there is one particular construction using n equals 1 theories. I mentioned it somewhere.
By J1.
Yeah. This one. So using this construction, you can compute the full superconformal index because these are Lagrangian theories, and you can compute them using matrix integral. So
If there's a pre-figurization, write down the W's. What are they? How do you compare them in that case?
For pre-filterization, you will have to actually match the R charges, and then you can, and then you can write down those W's.
Okay. Does the Hilbert series have a trace interpretation including that?
Hilbert series as trace. Well, of course, I mean the McDonald index itself is given by this trace. But
it's a 4-dimensional thing. But...
yeah, it's a 4-dimensional thing. The Hilbert series itself,
Hilbert index is just like a 2-dimensional curve.
Yeah. Okay. I see what you mean. So yeah, that's what I was mentioning here. This refined character. So actually, what we showed in this paper is that the refined character, which is defined as a trace with some filtration on the VOA, that refined character equals the Hilbert series, which is not a trace. Sorry?
T is a fugacity to the
Yeah. When you define the refined character, T appears as a fugacity for some other charges.
Which symmetry do you know? Do you have like some?
So yeah. So basically, you introduce a filtration on the VOA, and then that filtration introduces a bigrading. And with respect to that bigrading, you define the trace. So basically, it's like Q to the say W1 and T to the W2, where W1, W2 is the bigrading on the VOA. So I shouldn't say it's directly related to some symmetry, but it's like you introduce a bigrading and then you compute the trace using that grading.
Is the grading like compatible with like the conformal symmetry? Because usually when you have a grading, that's to think of it like it's a U1 symmetry, but maybe not in this case.
In this case, the bigrading is actually compatible with conformal weights of the VOA. Yeah, I guess that's all you can say. Like using the bigrading, the homogeneous spaces have the same conformal dimension and so on.
It sounds like you're saying that this VOA has some U1 symmetry that was not known before. Like T seems to be like capacity for some symmetry that was not identified. I don't know.
Yeah, I'm not sure if we can interpret it as some symmetry, but maybe there is a way. Yeah. I'll have to think about it. Thanks for the question.
I mean, there's no current.
Yeah. Well, if there are symmetries, you can introduce fugacities for it. But
Flavor symmetry.
Yeah, if you have flavor symmetries. But right now I'm putting all those to one. So I don't. Yeah. So I don't know if I can interpret these bigrading as coming from some symmetry. Maybe there is a way, but yeah, I'm not sure. I'll have to think about it. Okay, so that's the end of part one. This is one technique to compute the McDonald index using VOA. Now I'll explain another technique, but I don't know how I'm doing on time.
But I mean,
Okay.
we don't have a hard cutoff.
Okay.
But,
So yeah, so as I said, this technique it's a bit technical because you have to compute, you have to introduce all these arc spaces and Hilbert series and zoo algebra and so on. But it's very concrete in the sense that each step can be implemented on mathematical, and you don't have to do explicit counting of independent vectors and so on, because computing refined character requires you to do some counting. But here you can just implement everything on mathematical. And in some cases, as I showed, for example, in this case, you actually have some closed form expression. So now I'll explain another technique to compute the McDonald index. So let me start from what is known. So one can compute the Sood index from monodromy operator, which let me introduce what it is. So given a 4D equals to 2 theory, not necessarily conformal, they have moduli space, they have Coulomb branch, Higgs branch, and mixed branches. And Coulomb branch in particular is important because one can understand the low energy physics on the Coulomb branch exactly in most of the cases. We can parameterize the Coulomb branch by some parameter u, and the rank of the theory is basically the complex dimension of this space. I hope this R is not confusing because I also use the same thing for the U1 R chart. But this is just an integer R which gives us the dimension. And then at each point on the Coulomb branch, I have a charge lattice of the theory. And it is equipped with this antisymmetric pairing. And then I also have a central charge function. If I have a Seiberg-Witten description for the theory, then these things can be written down explicitly. But for these things exist for every 4D equals to 2 theory. Then I can also define these BPS indices, which takes a charge and gives us an integer. So this is basically counting the number of BPS operators with a given charge. I'll introduce it later.
Operator.
Right?
BPS states particle.
Yeah, BPS particles. And these indices actually obey wall crossing formula. I will not have much time to go into what wall crossing is, but what I mean is that on the Coulomb branch, there are several chambers, and those chambers are separated by walls of marginal stability. What can happen is if you cross a given wall, certain half BPS states can combine into quarter BPS or vice versa. Quarter BPS can break into 2 half BPS, and so this index will change if you cross a wall. And this wall crossing formula tells us how the index on one side of the wall is related to the index on the other side of the wall. So I'll have a little more to say about this later. So now I'll restrict to BPS sublattice, so charges which correspond to BPS operators. Now I've also dropped the U dependence, but it should be kept in mind that all these charges are at a given point on the Coulomb branch. So all these things depend on where we are on the Coulomb branch. And now these BPS particles are in irreducible representations of this group. So SU2L is the little group of the Lorentz group, and SU2R is the R symmetric group. This L and R is not left and right. This is little and R symmetric. So that's unfortunate, but okay. Now, given a charge gamma, we can look at the Hilbert space of BPS states with charge gamma. And then it has this general form. I can factor out a center of mass degree of freedom. This is basically just a free hyper. And then this takes care of the other non-trivial representation of the states of this group. And then I can define this protected spin character. This is one of those BPS indices. And it's defined as follows. So I take this internal space, and then I compute this trace. J here is the Cartan generator of the little group of the Lorentz group. And once I compute this trace, it can be expanded as follows. where all these omega and gamma, these are integers. And this index jumps across walls of marginal stability and obeys a wall crossing formula. Again, I'll not have much to say about this, but this is one of the conceptual bases for this conjecture that I'm going to explain. Okay, so now some more formalism. So given this BPS lattice, one can define this formal algebra by introducing formal variables x gamma for each gamma, and then equipping it with this product. So A is now this space equipped with this product, and then this is an algebra. Q here is again a formal variable, and it will be related to the variable in the Sur index later by the conjecture. Now one can define this quantum dilogarithm. For each z, you have this infinite product, which can be written as this sum. And this was the Pockhammer symbol, which I had introduced earlier. And with this definition, one can define this monodromy operator. So what we do is for each charge gamma, we take this operator u gamma, which is defined as follows. So we take those formal variables x gamma, and then we plug it in as the exponent of this quantum dilogarithm and raise it to this power omega n gamma. And this omega n gamma was defined here, coming from the protected spin character. And here this arrow means that one has to follow a particular ordering of multiplying these operators because they don't commute. So I have to tell you in what order to multiply. And this order is in increasing order of the argument of z gamma. Z gamma was the central charge function. So for each gamma, I have a central charge. And then I take the, I fix an angle theta, and then I just multiply them in increasing order in theta. So I go all around starting from a given theta. So once I have this operator, then I can define what is called this trace. So first of all, we look at these flavor charges, which are defined as follows. So those charges which have zero pairing with all other charges, those are called flavor charges. And then these flavor charges form a sublattice of the BPS lattice. So I can choose a basis for them. So gamma fi, this is a basis for the flavor charges. Then any given flavor charge can be expanded in this basis, where these fi gammas, these are integers. So then I can define the trace of x gamma. So x gamma was this formal variable that I introduced here. So I can define the trace of x gamma. This is just a definition as follows. So if this gamma is not a flavor charge, then the trace is 0. If it's a flavor charge, then this is how I define the trace. And now this trace of x gamma fi, which are the basis elements here, these will later be related to the fugacities in the Sur index. So for now, it's just some number, but later we'll relate it to, this conjecture will relate these traces to the fugacities for flavor symmetries. So this conjecture tells us that the Sur index of this 4n equals 2 SCFT of rank R, rank was the dimension of the Coulomb branch, is given by the following formula. We compute the trace of OQ with this extra factor, and this Z1 to ZNF, these are the flavor fugacities. NF here should be understood as the dimension of the, the rank of the flavor group of the theory. So this notation is because if I have a Lagrangian theory with NF hypermultiplets, then the rank of the flavor group is N. And this Z1 to ZNF, these will be related to these flavor fugacities. Again, this is theory dependent. Depending on the theory, you have to make a particular choice of this relation of these fugacities with these traces. And once you choose that relation, then you can compute the Sur index in this way. And the reason for this is that, so
the Q appears in the bottom dialogue.
Yeah. So this Q appears here, as well as like when I define this quantum dilogarithm, I have those Qs. And when I'm computing trace, I'll have to use this formula. So I'll have to arrange all those operators, like I will have to commute them and bring them into this form. Then I can compute the trace.
Right.
And to do that, I'll have to use these relations. So I'll have to combine charges into one operator here that will introduce some Q factors. So at the end, I'll show a computation and then it will be clear why this answer will be, this trace will be dependent on Q. Right, so, okay, so this is the conjecture. Now, left-hand side is the Sur index of the theory, which is defined for the conformal theory. But right-hand side, this operator is defined for any 4D equals to 2 theory. Like when I was defining it here, I did not assume anything about an SCFT. I did not use any information about the SCFT. All this is defined on the Coulomb branch at any given point on the Coulomb branch. So the reason why, the physical reason why this conjecture should work is that this OQ is a wall crossing invariant. So this OQ does not depend on the point on the Coulomb branch. You can compute it at any point and it will be the same operator. So right-hand side is computing something independent of the Coulomb branch. So even if you take it at the origin of the Coulomb branch, where you have a conformal theory, which is the conformal point, you should get some information about the conformal theory itself. And this conjecture is telling me that the information that you get is the Sur index of the theory. Again, I don't know of a proof, but this works. One can check this for a lot of theories. This works even for Lagrangian theories which are not conformal. I'll say something about that later. So now the next question that we can ask is, can we now compute McDonald index from the monodromy operator? That was the question that we asked earlier when we were computing Sur index from VOA. Now again, we ask the same question. And I'll again give you a very, very partial answer. The prescription that I'll give is very ad hoc. I don't know a physical reason why it works, but it works, it's experimental, it works, and there is a lot to be understood about it, the physical reason why it works. So, yeah, so before I move to that part, are there any questions at this point? All right. Okay, so to explain how to get the McDonald index from monodromy operator, I will have to introduce these BPS quivers. So for some 4D equals to 2 theories, the BPS spectrum can be given in terms of what are called BPS quivers. And examples where this works is this Rutgers-Douglas theories, which I had introduced earlier, these G1, G2 Rutgers-Douglas theories. And in particular, one class of these theories, which are these A1G theories, admit a source sink chamber. So I will explain what a source sink chamber is with this example. So take, for example, A1, A2N theory. Now, in a given chamber, there is a chamber in the Coulomb branch of this theory where the BPS spectrum is given by this quiver, this graph. What is this graph? So at each node, gamma 1 represents a BPS charge. And at each node, I have a free hypermultiplet. So basically, earlier I explained here that each space for a given charge, this space has a free hypermultiplet part and an internal part. But in this BPS quiver, at each point, I don't have any internal space. All I have is a free hypermultiplet. Now, what are these arrows? So arrow connecting gamma 1, gamma 2 is telling me the inner product, the pairing of this gamma 1 and gamma 2. So that pairing of gamma 1, gamma 2 is equals 1 because there is one arrow from one node to the other. Similarly, from gamma 2 to gamma 3, I have one arrow. So inner product of gamma 2 with gamma 3 is -1 because the arrow is reversed. So there are some rules which you can use to get information about the spectrum from this graph. And I explained 2 of those rules. One is that each node represents a free hyper with that given charge gamma 1. And then the arrows tell us about the pairing of the charges. Now, what are sources and sinks? So a node is called source if there are arrows going out of the node. And they are called sinks if there are arrows going in the sinks. So when I say that a theory admits a source sink chamber, meaning that its BPS spectrum is carried by such a quiver in which each node is either a source or a sink. So for example, here you can see the odd nodes are sources and the even nodes are sinks. Now such a quiver diagram is there for all A1G theories. And it's basically the Cartan, the Dinkin diagram of the Lie algebra G. So this is basically the Dinkin diagram of of A to N Lie algebra, but with some extra information of these arrows. These arrows here mean the pairing of the charges. Also, for each charge, there is also an anti-particle which has charge minus gamma, because these are lattices. So if gamma is in the lattice, minus gamma is also in the lattice. Another important fact about this BPS fiber is that the arguments of the central charges at this central charges for these gammas are ordered in this way. So if I have a gamma coming from a sink chamber, from a sink node, and a gamma from a source node, then it follows this particular rule. So the arguments of Z gammas are related like this. And this will be important when I'm trying to compute the monodromy operator, because the monodromy operator here, there is an ordering which depends on the arguments Z gamma. So this ordering will tell me how to compute the monodromy operator itself. Another rule is that all these formal variables X gammas, they commute if both of these charges are from sources or sinks. So this will again tell me how I can group the quantum dialogogrithms in the monodromy operator. So, and this I already explained that this pairing is determined by the number of arrows between I and J. So, for example, for this particular quiver diagram, the operator can be written as follows. First of all, you can see that I don't have any BPS index contribution here. So in this definition, I have this power here, omega n's. But as I said, each node represents a free hyper. There is no internal space. So that's why all these omega and gammas are 0, except for n equals 0. And so this entire thing just reduces to one term, which is EQ of X gamma. That's all. And this is what appears here. So these are now sources, sinks, and they are ordered in this way because of this relation. So the good thing about this BPS quiver is that it just makes the computation of this operator extremely easy. Now, this is the final thing. The prescription now tells us the following. So now define these new operators. These are some deformation of the quantum dialgorithm. All I have done is introduce a capital T here. And then I also define this E tilde with a capital T introduced in the denominator here. And then the prescription for a new operator. So what I want to do is I want to define a generalization of this OQ of this operator. So what I do is in the expression here, I replace EQs as follows. So if I have a source node, I replace EQ of X minus gamma by EQT, which is defined here. If I have a sink node, I replace it by EQT tilde, which is defined here. And again, for plus charges, I replace EQX gamma by EQT, but the sinks I leave as it is. Now again, as I said, this is very ad hoc. We don't know why this works, but if you take this rule, then you can define this OQT, right? Because I have replaced by EQs by EQT. You have these new operators, and then you compute the trace by the same rule that I explained earlier. And the conjecture is that it will give you the McDonald index of the theory with this extra factor. And what is the relation between this capital T and the small t earlier? This is the relation. And the Sood limit is now just capital T going to 1, because that will mean small t going to small q. So if you look at these formulas, if you take capital T equals 1, this reduces to the original dialogogrithms. And so if I take T equals 1, I just get the original monodromy operator. And so this trace will just give me the Sood index by Cordova-Shaw conjecture. So this generalization, this conjecture gives us the McDonald index, and the Sood limit of the formula is obvious from the Cordova-Shaw conjecture.
This thing's supposed to be like a wall crossing?
That's one question, yeah. So because this is computing the McDonald index, for these examples at least, we can ask the question, are these operators wall crossing invariant? We don't know. Like, we would like to prove it that it's a wall crossing invariant, because this gives some evidence for that, but we don't know how to prove such a thing. Yeah, and this works only with theories, for theories which have sourcing chambers. And again, that's a very restrictive condition. we would like to generalize it to general theories, but that will require us to understand what these functions mean and what is this replacement doing, what does this mean physically.
When you say that it's a very restrictive condition, I mean, I understand in terms of the quiver, but in terms of the real Coulomb branch of the theory, does it also have a very sort of simple structure in terms of changes on the Coulomb branch? And
Yeah, so I mean, so this prescription works only if we have a sourcing chamber. If we don't have it, then we don't know how to define this OQT. So I have the entire Coulomb branch geometry. I know how to define these OQs, but I don't know how to define this OQT unless I have a sourcing chamber where I can do this prescription. Because I need sources and sinks and so on.
but the statement of the sourcing chamber was like some very sort of highbrow condition about the quiver. What does it actually tell you about the Coulomb?
Yeah, I mean, from the quiver, the definition is simply that you have these based on these arrows. But in terms of the Coulomb branch, I don't know what it really means. If we can track the meaning of these arrows in the Coulomb branch itself in terms of things which are defined on the Coulomb branch, then probably we can understand what these things are doing. But yeah, that is
So that's also not known.
yeah, that also. But yeah, the hope would be that we understand how to first get out of the sourcing chamber, or at least understand physically what sourcing chamber means in terms of these functions, and then maybe we can generalize it to general theories. So, so this is some computation. So I can now try to give some evidence for this conjecture. And the first computation that we can do is for A1, A2n theory, because here the quiver is this. I have it in the sourcing chamber. I have the operator. To define the new operator, all I have to do is replace these EQs with EQTs and EQ tilde T's. So that's what is done here. I have this new operator. All I have done is at sources, I have replaced EQs by EQT, and at sinks, I have replaced it by E tilde QT. Okay. Once I have this operator, then what I want to do is put the explicit expansion for these EQTs, and this is what I get. So this complicated expression is just coming from this definition of these functions. So for each of those, I have an index, which are these indices, and they are all summed over. You get this complicated expression. Here, this bracket Q simply is this notation. So this is basically Q K 2I minus 1. And then you have these operators, the formal variables here that we have. Now, to compute the trace, we will have to combine them together. We have to combine these charges. And there is some manipulation that you have to do using quantum torus algebra. So you take all these and then you combine them into one using the quantum torus algebra. You get some factors of Q from here, actually. So this is what I was referring to earlier. When you commute them and combine them, you get some factors of Q. And here, C is the Cartan matrix of A2n. Again, one can use quantum torus algebra to combine these two. That's what we do here. You again get some power of Q. That power is not important right now. What we find is that the trace is of this X with this gamma. Now the point is for A1, A2n theory, there is no flavor symmetry. So there are no flavor charges. So this trace will be 0 unless this gamma is 0. So that gives us these delta functions. Okay. And this power of Q actually depends on KI-Li. When you take KI-Li to be equal, this power just vanishes. So all you have is this delta function. You replace that and you get, after some simplification, you get this formula for the Macdonald index of A1, A2n theory. You can see that if you take capital T going to 1, you should get the Sood index. So that will give us some new Q series identity. In fact, there is a general Q series identity. This is the formula that we get from this prescription, and this is the known Macdonald index of the theory. So you get this identity in Q and T series, and this can be proven rigorously. So that's one test of this conjecture. And another, so this reproduces the Macdonald index for all A1G theories that has been checked. And there is one more example, because here I did not explain one part of this proposal, which was that if you have a source node with valency greater than 2, meaning that if you have a node where there are 3 arrows coming in or going out, then what you do is exchange the roles of source and sinks and apply the above procedure. And for that, this is one example. So here gamma 3 has valency 3, 3 arrows are going out of it. So now what you do is reverse the roles of source and sinks. Once you do that, you get this OQT, and then you compute the trace. And this theory has U1 flavor symmetry. So there is a flavor fugacity Z for this U1. And this is the relation of the flavor charge in terms of these charges here. This is again coming from Cordova-Shaw. And this is the relation of the trace of the flavor charge with the fugacity Z. Once you plug this in, you get this formula for the McDonald index. Again, it's some computation. It looks very complicated, but it's actually very easy to do. You get this formula. And as far as I know, there is no known McDonald index for A1 E7 theory. So this is like a new conjecture for the McDonald index. If you expand it, it looks consistent. But yeah, we don't know any paper which has computed it to match it. So this is like a conjecture for the McDonald index. But for other
no class S construction of this?
I think there are constructions in classes, but yeah, I haven't really found the computation using that construction. I mean, the Sood indices are available, and of course, it gives us the correct answer. But McDonald index itself, or even the Hall Littlewood index, which would tell us something about this T dependence, that also we couldn't find in the literature. And of course, for all other A1G theories, some answers are known in various papers, and you can compute and match that all of them match. All of them give you the correct answer. So yeah, so now let me just tell you what are the limitations of these two approaches. So the VOA approach, as I said, this determination of this weights WX size is not known now. And this is related to the R filtration problem. There have been some progress in these papers. And this other monodromy operator approach works only with the sourcing chamber, as I explained, and we don't know how to generalize it. And the Cordova-Shaw prescription actually works even for non-conformal Lagrangian theories. For Lagrangian theories, you can write down the superconformal index in terms of a matrix integral. And you can also compute the trace because the monodromy operator is defined for any Fourier equals-to-2 theory. And you can check that they match. But I try to check this prescription, this conjecture. So I can write this down even for a Lagrangian theory or non-conformal theory as long as I have a sourcing chamber, and there are examples.
What is the left hand? The left hand side is not defined.
Well, if it's Lagrangian theory, then I can write down a matrix integral for it.
No, you need the U1R symmetry. The U.
Yeah. But
You mean a superconformal Lagrangian theory?
yeah. Sorry.
Oh.
I mean, well, actually, no. I can even take non-conformal Lagrangian theories. All I need is that. So for conformal theories, you can compute the index using this matrix integral, which you can just compute it at the weak coupling, and then everything reduces to a matrix integral. The matrix integral itself is defined for any theory because it does not care about.
That's only true in the Schur index. It's not true for the McDonald. For the Schur index, it's true, and it's known that the matrix. So for the Schur index, because the little r drops out,
Yeah.
there's an obvious kind of sense in which maybe you can just continue the same calculation. That was conjectured and used by many people.
Yeah.
And then you can prove it.
Okay.
But in the McDonald index, you explicitly have the fugacity coupling to little r.
Okay.
And this is a symmetry which is just explicitly broken in the non-conformal case. So you can formally write down the matrix model, but
Yeah.
you know,
Yeah. But
there's
I
no
mean,
sense in which it should.
it will not give anything sensible. You will have negative coefficients and
Right.
weird kind of things.
So that's what you're comparing with here.
Yeah. So I guess even comparing that is not sensible. So
And the fact that you don't get a good match
it doesn't match.
doesn't
So
mean that the right.
doesn't mean that this is of course, yeah. But yeah. Actually, there is one example in which it works, and so there is one example in which one can compute the matrix integral as well, and it does match with this proposal.
Which one?
It's the it's the QED. So U1 gauge theory with one hierarchy. And there it works.
Probably too simple because it's basically a free hyper.
Yeah.
The fact that it's QED is not that.
Yeah. It's like it's not difficult. It's kind of trivial to check that it works. But in any sensible example, for example, SU2 with one flavor or two flavor, doesn't work at all. Yeah, but okay, yeah, this does not tell us anything about this conjecture, whether it's sensible or not, because as you just said, left-hand side does not make sense.
Well, if you had an independent argument that this O was a wall crossing invariant, that would give you some more confidence that the right-hand side makes sense always.
Yeah. Yes, I mean the right-hand side, as long as I have a sourcing chamber, I can always define it. And the trace will give me something. Whether it will be something sensible in the theory itself is not clear.
But even in theories with a sourcing chamber, I thought you said that you don't know how to prove that it's a wall crossing.
Yeah, okay, yeah, that I don't know. Yes. So I guess that was one of the questions here. So does this new operator OQT give us some new wall crossing formula? That's one of the questions. Whether it's a wall crossing invariant. And then, okay, one other question is to generalize this monodromy operator prescription to general for equals to 2 SCFTs. And then can one prove this using this 3D TFTs? Because there was a recent paper where they were able to get these formulas using some 3D TFT picture. I don't understand the full picture, but there's a way you can get those formula using 3D TFT. So can one prove this conjecture using 3D TFTs? That's the question. Yeah, and with that, I'll end. Thank you.
The 3D TFT approach, that's like where the BOA is at the boundary or something?
Yeah.
But it relates to the monodromy approach you're saying.
Not
just want
directly from monodromy approach, but so what happens is that they can compute this this form of the McDonald index using 3D data. They don't have to go to monodromy operator.
The 3D data of what 3D?
So there is a 3D n equals 4 Chern-Simons theory that they can construct by starting with a 3D n equals to 2 Chern-Simons matter theory, and then flowing to IR, constructing some rank 0 theory, and then they twist. And then after twisting, you can compute these half indices and they somehow match with the Sur index. They can make a generalization there. So rather than computing the half index with just one fugacities, there is some way in which you can introduce another fugacities for some other symmetry of the theory. And that seems to compute the McDonald index.
But this is not somehow trivially related to
the
40, just some other.
Yeah, some other construction. The point is that the formula they get has this particular form. So that's why it might be useful to understand, but yeah, I don't understand it very well.
Is there some class S argument for why these two things should be related, or it's just like it's like a random guess that you start with?
The construction itself seems random, but the answers that you get actually are related to this SCFT BOA correspondence. So so you start with the 3D theory, there is a way you can get a 2D view. And there was a recent paper which explained that you can start with 4D theories and do some compactification to get this 3D theory itself. So then it is kind of an intermediate step in this SCFT BOA correspondence.
When was this paper?
So this was by Dedushenko, I think 2D, 4D correspondence, something like that. I don't remember exactly the title. But yeah, it was compactification of 4D n equals to 2 theories on some cigar geometry, which gives you this 3D TFT that is related to the VOA. So it's like an intermediate step. That's it.
Other questions? All right, thanks.
Thank you.